Okay, so this is lecture 13. In this lecture, we're going to discuss error detection and error correction. In dealing with computers, when you send data stream of zeros and ones, there should be some way to make sure the data is correct. And if an error occurs, how could we correct it? So now we're going to discuss techniques to detect errors and to correct them. Two different techniques are usually tackled in such a field. Techniques with which you detect errors like the parity, the checksum, the cyclic redundancy check, CRC, and techniques to correct errors, and we are going to discuss the Hamming code. So we have three techniques for error detection and one for error correction. Okay, in error detection, the system is halted and you have to redo the operation from the very beginning because an error occurs and we don't have the mean to correct it. While in error correction techniques, if you use error correction techniques, your system will correct the error and continues its operation. The first error detecting technique is the parity check. And usually it is used to check a single bit error. If an error occurs in a single bit, so the data is incorrect and you have to ask the sender to resend you the data once more. And what this parity check does is this. You have a byte of information. It adds a single bit to every byte to be sent. So your message is a byte and the parity check adds one additional byte to the message. So now you have 9 bits. This additional bit is either a 0 or a 1. Okay? It is a 0 or a 1. And we have two types of parity. Even parity, which means the total number of ones in your message should be even. So you have a single byte, containing certain number of ones. Let's say this number of ones in your original byte is odd, 3 ones, and you are using even parity. You're using even parity. So you add a ninth bit, which should be 1, to make the whole number of ones inside the 9-bit word an even number. Okay? And if the message, the original message, contains an even number of ones, let's say 4, this 9th bit is made 0, so the total number of ones in the 9-bit word should be even if we are using an even parity. And we do the opposite with odd parity. And there is an integrated circuit which is used to generate and check the parity. If you feed to this integrated circuit 8 bits and you configure it for the even parity, all right, it gives you 9 bits correctly. Okay, and if you feed to this integrated circuit 9 bits, it gives you 8 bits and tells you whether this byte is correct or not. So it is used to generate and check the parity. Good. And it generates even or odd parity. So the same integrated circuit can be configured to use an even or odd parity. Good. And it also checks for an even and odd parity. Another technique known as the checksum. Okay. So you check a block of characters. For example, what this does, this checksum, when you send a data byte by byte, okay, it takes, let's say, a few bytes, 4 bytes, add them together, and send with these 4 bytes a fifth byte containing the two's complement of the sum. And at the receiving end, if you add the two's complement of the sum to the sum and you get a 0, it means these 4 bytes have been received correctly. So it sends along with a block of data composed of some number of bytes the two's complement of the sum of these bytes. And at the receiving end, if you add the two's complement to the sum and you get a 0, this is an indication that the data, the sent data, have been received correctly. Okay, good. For example, if you're sending these 4 bytes sequentially, 10, 23, 45, 04, you sum them up, you get 7C hexadecimal, or this is in binary. You do the two's complement. Two's complement, you go from the least significant to the most significant. You leave the first one you meet, then you complement the rest. So this is now your two's complement. Converting to hexadecimal number, it's 84. So now you send the 84 as your fifth byte with these data. At the receiving end, you add the sum of the sent 4 bytes to this two's complement. Disregard the carry. If you get a 0, it means these 4 bytes have been received correctly. This is the checksum. Otherwise, your data is incorrect and you would have to ask the sender to resend you the data again. All right. Of course, the third technique used to check errors is the cyclic redundancy check. What does this technique do will be discussed in a moment. Usually this is used to check data transfer to the hard drives of your computers. And it treats your data as a stream of bits sequentially, coming to your disk sequentially of n bit long. All right. These bits are used as coefficients of a characteristic polynomial mx. For example, your least significant bit, the zeros bit, is a coefficient of x to the power 0. Your b1 coefficient to x to the power 1. b2 coefficient to x to the power 2, and so on. Your bn is a coefficient to the x to the power n. Good. For example, if you have a 16-bit data stream like this one, okay, so now this 0 is the coefficient of x to the power 0, x to the power 1, x to the power 2, x to the 3. They are all 0. The first term to appear in the characteristic equation, x to the 4, to the 5, to the 6, to the 7, no x to the 8, x to 9, x to 10, no 11, no 12, x to 13. And this would be your characteristic polynomial. 4, 5, 6, 7, 9, 10, and 13. Okay, so if you have a message, this message can be converted into a characteristic polynomial as such. Good. Then, along with this characteristic polynomial, there should be another polynomial called a generator polynomial. Okay, and this generator polynomial should be known to both the sender and a receiver. So the receiver and the sender should agree on some generator polynomial g of x. Okay, good. And here are well-known generator polynomials. This is a generator polynomial named CRC12, CRC16, CRC-CC-ITT, composed of 16 bits, CRC32. All right, so you and the receiver have to agree on one of these generator polynomials. Okay, how would we calculate the CRC? CRC are certain number of bits to be appended to your message. So you send your message to your receiver appended with additional few bits called the CRC bits. You send them, the receiver will receive the message along with the CRC and will do the CRC for the whole message. If the receiver gets zeros in place of these additional bits of the CRC, this means the original message is received correctly. All right. So what you do is this. From your message, you get the characteristic polynomial. You multiply it by the order of your generator polynomial, x of n. You divide by the generator polynomial, you will get a quotient and a remainder. These remainder number of bits are to be appended to the original message. So this is your original message. If your generator polynomial is of degree 3, meaning you have to append 3 bits, which are the result of this long division process. Okay, let's take an example. So this is now a commonly used generator polynomial. The remainder Rx should be appended to the original message. At the receiving end, you do the same with the message appended with the CRC. If the remainder you get at the receiving end is 0, this is an indication that the message has been received correctly. For example, here, this is your message. Okay, this is your generator polynomial. Good. The generator polynomial x0, 1, 2, 3 of degree 3. Okay, so you have to first append the original message with 3 zeros. This is equivalent to multiply mx with x to the power 3. Okay, you append 3 zeros and you do the long division. The message with the appended 3 zeros divided by the generator polynomial. And you do this long division. Here is the quotient and here is the remainder. You append the 3 bits in place of the 3 zeros. You append your original message with 101. If this process is redone at the receiving end and you get a remainder of 3 zeros, this is an indication of a correct reception of your message. An easier way to do this, instead of doing long division binary and binary long division, we can do this. This is your message. This is your generator polynomial. Okay, get your characteristic polynomial from the message. So 0 multiplied by x to the power 0, then 1 multiplied by x to the power 1, then 0, x to the power 2, then 1, x to the power 3, then 1, x to the power 4, and so on. So you will get this characteristic polynomial. And you have your generator polynomial, again, which is equal to, you convert this to your polynomial. These are to be used as coefficients. And this is your generator polynomial of degree 3. So you do the long division now, which is x to the power 3 multiplied by mx times gx. You get a quotient and a remainder. Remainder is to be appended to your original message. So here is your x cubed times mx, and here is your generator polynomial. All right? So x10 over x3 gets an x7. You multiply x7 by this, you will get this, and you do your subtraction in a special way, as if you are XORing. Similar terms are cancelled, x10 and x7, and you write the rest without paying attention to the sign. So the rest is x9, x6, x4. x9, x6, x4. You do again the long division, x9 by x3, x6, you multiply, you XOR, similar terms are cancelled, you get x8, x4, then you divide x8, x3, you get x5, you multiply, you do XORing, similar terms are cancelled, you get x7, x5, x4, and you continue till you get to the x3 over x3 gets you a 1. You multiply, you get this. So this is your CRC bits. It's a polynomial of degree 2, no x1. So the coefficient of x1 is 0, x0 is 1. So these are the 3 bits to be added, to be appended to your original message. So now you have the message appended with the CRC. Okay, you do this at the receiving end. If you get 3 zeros in place of this 1, 0, 1, this a good indication to you, which means the stream of bits representing the message have been received correctly. Good. Now, the Hamming code. So this is a technique with which we can detect and correct the error. So you have a message at the receiving end. You can check whether the message is correct or not. And if your message is incorrect up to a single bit, you can correct it. So if in transmitting a message, one bit is flipped from a 1 to a 0 or a 0 to a 1, this Hamming code can detect it and correct it. Good. And the main objective is to correct only a single bit error in a message of 8 bits, a byte. Good. So first, your byte will be labeled. These are the 8 bits to be sent. We label them x3, x5, x6, 7, 9, and 12. So this is your least significant bit, and this is your most significant bit. Then we use 4 parity bits. We label them 1, indicating 2x, 2 to the power 0, then 2, 2 to the power 1, then 4, 2 to the power 2, then 8, 2 to the power 3. Good. And we assign some number of bits from your original message with each of these parity bits. For example, for the first parity bit P1, we assign x3, x5, x7, x9, x11. While for P2, the second parity bit, we assign from the message bit 3, 6, 7, 10, 11, 4, and 8. And if you notice what's common between 3, 5, 7, 9, 11 assigned to P1 is that the bit whose weight is 2 to the power 0 is 1. So the least significant bit is 1 in 3, 5, 7, 9, 11. While here we assign the number of bits whose 2 to the power 1 bit is 1. For example, 3 is rated 1, 1. So 2 to the power 0 is 1, and 2 to the power 1 is 1. This is why you find 3 in both P1 and P2. 6, yes, the bit whose weight is 2 to the power 1 is 1, and so on. Here, 2 to the power 2 is 1. Here, the bit whose weight is 2 to the power 3 is 1. This is how they go, the parity bit. And if you are using even parity, you count the number of ones in these bits. If it is this number of ones is an even, you assign 0 to P1. If it is an odd number of ones, you assign 1 to P1 to make them even. Okay, so let's take an example. Good. Okay, let's take an example. Here is the message composed of 8 bits, and we assume that we are going to use even parity. Here again we list the bits to be used with each of the parity bits. Good. And we place the message least significant, most significant as such in positions 3, 5, 6, 7, 9, 10, 11, 12. We leave 2 to the power 0, which is 1, 2 to the power 2, which is 2, 2 to the power 1, which is 2, 2 to the power 2, which is 4, 2 to the power 3, which is 8. So we leave these 4 positions for the parity. Now, how do we calculate the parity? P1, do we place a 0 or a 1 in P1? We go and check the message in the 3rd, 5th, 9th, 7th, 9th, and 11th positions. We count the number of ones there. If the number of ones is even, we place a 0 in P1. If it's odd, we place a 1 to make it even in P1. So let's go now. The 3rd position, we have a 1. The 5th, so 2 ones. The 7th, 3 ones. The 9th, still 3 ones. The 11th, 4 ones. So the number of ones in these positions counts to an even number, 4 ones. So we don't need extra ones. So we place a 0 inside P1. How about the parity bit number 2, bit 2, P2? We'll go and check these positions. Okay, 3, we have a 1. 6, we still have a 1. 7s, 2 ones. 10s, still 2 ones. 11s, 3 ones. So these contains 3 ones, which means an odd number of ones. We need an extra one to make them even. So we place 1 in P2 and so on for P4 and P8. Now the message to be sent with the parity would be 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0. So place these 4 parity bits in their positions. So this is your parity encoded data. 0, 1, then 1, and so on. Okay? Suppose that this sent data is incorrectly received and this specific bit flips from a 0 to a 1. Okay, so we take this message and redo the Hamming code over the whole message in order to detect this error and correct it. Good. This is again P1. All right, and we have an additional position in which a bit was placed from P1. So we should take this into account, the 1, the 2 position, and the 4 and the 8. Again, these positions in decimal numbers are picked because the coefficient of 2 to the power 3 in each is equal to 1. Good. So we place the 12 bits inside our table, okay, and they receive the message. This is the received message according to their positions, and we do recalculation of the parity bit. You would find that P1 is a 0, P2 is a 1, P4 is a 0, and P8 is a 1. 8 is the most significant, 1 is the least significant, so you have an error in the bit whose position is 1, 0, 1, 0. So the bit in position 10 is incorrect. This is position 10. This bit is incorrect. You correct it, you flip it. If it's 1, make it a 0. If it's a 0, make it 1. And this is how do we detect and correct errors using Hamming code. And this is the end of lecture number 13. We see you in lecture number 14, inshallah. Thank you.